All right, let's lock in, everyone. We have the penultimate lesson. That means the next lesson is going to be awesome. All right, okay. So we're learning to solve logarithmic equations today, and we're doing a lot all right away with like logarithms, okay? So one thing I want to do is for the visual learners here, I want to get you to visualize a logarithmic graph. If you recall, logarithms are the inverse functions to exponential functions. And exponential functions generally, like when we have like say something like 2 to the x, okay, we could have 1/2 to the x or something. It'd be reflected through the y-axis, but I'm not going to talk about this for too long. It's going to look something like this, right? Well, if I reflect a function through the line y equals x, then I get the reciprocal function. And so the reciprocal function here would look like this, like that, okay? Something like that, okay? So now some things to say about this. Domain and range flip to become range and domain of your inverse function, right? So this one has x can be of the reals, and that's its range. Sorry, that's its domain. It can literally be any input. The same as this one here has a range of y is of the reals, okay? Y can be any number for these ones. But up here, y is strictly greater than 0, right? This is asymptotic to the x-axis that way. Same way this one here is asymptotic to the y-axis. So that is to say x is strictly greater than 0. And we're going to be using that fact today when we're solving logarithmic equations and noting which solutions we have to throw in the garbage because they nonsense. Okay, can you tuck the door closed? And don't forget to turn the light off. Okay, so let's go. All right, so we're going to do these things. Let's go. So recall our laws of logarithms. Depending on the complexity of the algebra you're solving, you may need any number of these, okay? So if you have like logs with the same base and you're adding them, you can multiply the argument of the logarithms, okay? Those can multiply there, all right? This should be in your notes already. This is just a quick review. Similarly, if you're subtracting one log from another, you can divide the subjects of those logarithms. And this is the money one, right? This one we use so often because we can get an unknown exponent down at the level of multiplication down there. And then we have the change of base rule. We're not going to see that one today, but you may. And then here, if log a of x is equal to log a of y, then x is equal to y. This is analogous to saying like if I had 2 to the x equals 64, you could write 64 as 2 to the 6. And so if 2 to the 6 equals 2 to the x, then our next line would be equate the exponents, okay? That's exactly the same thing that you're seeing there because the logarithm is the exponent. Like we're just manipulating the form so that we can do things to it. Okay, so that's the equality rule. So add this to your notes. So when we're solving logarithmic equations, our strategies are going to be, we want to start by stating the restrictions, okay? So the restrictions on our logarithms, if we have log base A is x and that equals y, okay? Then y can be whatever it wants. We can have anything in the exponent, but x is strictly greater than 0, and the base of our exponents are also greater than 0. We won't see this one come into play very much in our working, but this one is going to show up a lot. You're going to use this a lot. All right, the next thing we want to do is express both sides of the equations in terms of a single logarithm with the same base. This is similar to manipulating the base of an exponential equation on both sides so that you have the same base number, and then we can solve by using the definitions of a logarithm. So the definition of a logarithm, if we have something like log base A of x is equal to y, then that rearranges into a to the y equals x. Okay, so we can use this to solve these types of situations, or we can use log a x equals log a to the y. When you have two logs of the same base, then their arguments are equal, if they're equal. So we're gonna see how we use both. Are you ready to see some examples? So, and then we already talked about these restrictions. Okay, these two are both greater than 0. So I would suggest that you state your restrictions early in your working so that you don't mistakenly say something nonsensical, like something outside the domain of a given function is one of the solutions, when it's clearly like just a total blank space on the graph. So let's go. If we have this one, go ahead and copy it down. Log base 5, 2x minus 4 equals log base 5 of 36. What's our restrictions on x? Well, anyone tell me? Yeah? X has to be what?
Restrictions on x?
Yeah.
Is it 2?
Well, what's special about 2? What's the relationship between x and 2 and the domain of this function? Okay, so here's how we could do it. We could say 2x minus 4. You're absolutely right. 2x minus 4 has to be greater than 0. And this reminds me of something that you might remember from Unit 3. So we say 2x is greater than 4. And that simplifies to x is greater than 2. Great job, Charlie.
Thanks.
Yeah, so x must be greater than 2. So if we were to graph something like that, it would look something like this, right? You'd have this thing coming down there. All right, like that. Okay, fine. And that would be our asymptote, would be at x is 2. So this is x equals 2. Okay, but you're not going to, you will graph these later. All right, so now we can just go ahead and, what property do we use to solve for x? Well, if we have log same base, same thing equals log same base, different thing, then these are in fact not different, they're the same. So we just equate those things. 2x minus 4 equals 36, and that gives us x equals 20. Since x equals 20 is bigger than x is greater than 2, it is a proper solution, and the people rejoice. And get full marks, everyone. I know what motivates you. Okay, any more questions about that one? Probably not. It's pretty straightforward. Okay, let's go. Write this one down. Copy this one down on your lined paper or blank paper. Log 3, 12 minus log base 3x equals log base 3, 3. Well, what do you think? No. So here, x must be greater than 0. Beautiful. So there's our restrictions. What can we do with that whole thing? Yeah? Yes, good. So we apply that logarithm property. So log base 3 of 12 over x equals, do you want to keep that or manipulate it? Sorry? You want to manipulate it? Both are fine. If you manipulate it, you can just, do you know what log base 3 of 3 is? Kunal's telling me it's 1. That's very good, Kunal. Okay, Kunal says that if you raise 3 to the power 1, you get the value 3. That's very good. Okay, so I don't mean to like make fun of you or something. It's actually very good to point that out because it's new, right? It's like a new fluency skill. So you have it, so very fast. Good. So if that's 1, now we can use our whole thing here, which is to say 3 to the power 1 equals this. So write that out. 3 to the power 1 equals 12 over x. 3 to the power 1 happens to be 3. So then this can rearrange and give us x equals 4. Do you agree? I hope you agree. Do you agree that x equals 4 is greater than 0? Sure. Yeah, that's fine. You also don't have to manipulate it at that point. You could say log 3 of 12 on x is equal to log 3 of 3, and then equate these two things, which is, you'll note, exactly the same thing as we have there. It's just like, It's a little bit like saying you can turn left and then go straight, or you can go straight and then turn left, and you kind of end up wait and then turn right. Never mind. It's just different directions to the same place. Sometimes I come up with the best metaphors. It's like something else when I do that. Okay, how about this one? What can't x be? Kuno. X is certainly greater than 12 because this thing has to be greater than 12. So you could write that out and algebraically manipulate. But I also note that x must be greater than 0. So this is like one of these situations where you got 0 on your number line and you got 12 on your number line, and it must be both greater than 0 and greater than 12. It must be both of those things. So that is to say it must be greater than 12. Right? Right. Yeah. I'm spelling that out and really taking my time because they're going to get more complicated than that. So that's how you think about those. What do I do here when I'm adding two logarithms together? I multiply that thing inside. So we have log 4 of x times x minus 12 equals 3. Okay? And now, what we get is it's just a thing of beauty, everybody. It's just so pretty. Watch this. How are we going to solve that? Hayden, what do we do to take it to another level? And don't say queen to e4. Not sure, right? Oh, okay. Someone shame him. Shame him for me. Okay, yeah, Kunal? Sure, yeah, we can do that. We get log 4 of x squared minus 12x. Put that in brackets because it's all the argument of that log equals 3. This is it. Remember, we can do log ax equals y. We can turn that around into a to the power y equals x. This is the idea that we're going to use next. Was that what you were going to say, Luke?
No.
Or you're just stretching?
Yeah,
Okay, just working out your throwing arm, eh?
I guess so.
4 to the 3 equals x squared minus 12x. People are saying, you say this is the penultimate lesson and next lesson gets better, Mr. Jennings? How could that be? How could that be, Mr. Jennings? I ain't going to have any shade left to throw.
The square root plus x. No.
No.
Is this like where you subtract? Oh, wait, no.
Huh?
I mean, you could subtract 64 and then do quadratic.
Yes. So we set it equal to 0. Almost like we've been doing this for 3 years. 0 equals x minus 16 times x plus 4. Let's just do a quick check. X squared plus 4x minus 16x is indeed minus 12x minus 64. Okay, that is algebraically equivalent. And then what did we forget to, oh, we did remember to do it. X is greater than 12, everyone. So what value is x? X equals 16. X equals minus 4 is what we call an extraneous solution. This one is smiley face solution. Questions about that one? Yes, we can find ways to practice our grade 10 skills too. All right, now how about this one? Someone help me out. Someone from the back table, tell me the restrictions on R. Yeah, I was going to say Jesse, but then I thought back table. Spread it out a bit. There's a bit of senioritis going on back there. So what must R be greater than, less than? Charlie did a great job before. Charlie, just send them brainwaves. Oh, here he comes. Here, what you got?
It has to be more than 6, and it has to be more than 14. Wait.
Yeah.
Wait.
Has to be, well, just the other flavor of
Yeah,
14.
yeah.
Yeah, so you gave me vanilla. It's actually chocolate. So, so here, r has to be greater than minus 14, and r has to be greater than minus 6. So this is really the only one that's at play here. And now, what do you want to do in this case? I got 2 multiplied by the logarithm of that is equal to the logarithm of that. Yeah?
You put 2 as the power of r minus 6.
Beautiful. So we have log base 2 of r minus 6 all squared equals log base 2 of r plus 14. And then what, Kunal?
You can do r minus 6 squared equals r plus 14.
Sure. Are you okay if I write out r minus 6 squared like this?
Yeah.
Am I right or am I right? I'm right, eh?
And then you can
Yeah.
just
Never doubt me.
make it equal to 0.
And then make it equal to 0. So we have r squared minus 13r plus 22 equals 0. What values of r make that true?
Well, 11 and 2. Yeah, I got negative 2.
11 and 2, good. Yes, so we have r minus 2 and r minus 11 is our factorization. So what do we get for solutions that falls within this domain?
2.
Must be greater than 6.
R11.
R equals 11. R equals 2 is extraneous.
You have to write that first.
Yeah. Let me get back to you on that. I think it's fine if you don't, but okay, so here's another example. So I'm going to pause on this one, give you a chance to work it out, and then we chat again. Go. Practice. Oh, wait. Okay, let's take a look together, everyone. So this is what my work looks like. What does your work look like? If your work looks like this, you too may be on the path to a nice mark after midterm. Ha! Yeah. So, we note the restrictions on x. X must be greater than 0 here, but 7x minus 3 must also be greater than 0, which means x must be greater than 3/7. When we apply power law here and bring that there, we get this. And then when we're adding exponents, we're going to move that in as multiplication. Beautiful. Okay. And then now we're 2 logs with the same base, so we can equate their arguments, this one and this one. Equating those gives us this quadratic when we set it equal to 0, which factorizes this way, which gives us these 2 solutions. Both are greater than 3/7 for reasons previously discussed. 3.5/7 is 1/2, so 1/2 is greater than 3/7. You'd rather have half of a chocolate bar than 3/7 of a chocolate bar, unless you're a dog. Okay, let's keep going. Huh? Oh, yeah, it is. It's great. Yeah. So, right away, we know x must be greater than 1. Here, x is greater than 1, and then we just keep going. So, you said a difference of squares. I love it. We have 2 logs that are adding, so we multiply their arguments. X plus 1 times x minus 1 makes a difference of squares. That's log 8. Okay. This is to say x squared minus 1 equals 8. This thing, when we multiply it out, gives us that. And now we equate the arguments. X squared minus 9 equals 0 is one way to do this.
Or x plus 3 or 2x.
Yeah. So did you say x plus 3, x minus 3? Is that what you would do?
That's no 2x values, yeah.
Yeah. Okay. Cool. Yeah, so x equals plus or minus 3. The other way to do it is from here, send everything to the other side. X squared equals 9. You square root both sides and you get x is equal to plus or minus 3. You don't have to do this fancy stuff. You just got to get to here. But then once we're there, we got to throw one in the garbage. Which one you want to throw away? Negative 3 is total garbage. Oh my goodness, it's so fast. The lesson ends so quickly. X equals 3. X is minus 3 is extraneous, so we might not even write it down. We'll get back to you on that. Okay. How about this one? Oh no. Oh no, this one got good. Wait, do we want to do this one? Yeah, sure, let's do it. Okay.
X was 5.
So we have 3x squared is greater than 3. So x squared is greater than 1. So that means x is greater than 1. Or x is less than 1 also works. Sorry, less than negative 1. There. So that would satisfy this one here. So there's our two things in our domain. So that would look like this. Here's 0. Here's minus 1. And here's 1. And these are the values of x not inclusive. And here are the values of x not inclusive that are valid there. So that's our number line. Look at it. Okay. So, but we also have this must also be positive. So x plus 5 is greater than 0. That means x must be greater than negative 5. So actually we have down here at negative 5, like it stops there. Okay? So that's the domain that this thing has solutions in. This little interval in there, non-inclusive between minus 5 and minus 1, and greater than 1. All right, so let's see what we get. What's our strategy to solve this one? Yeah?
I would change the form
Okay.
to x plus 5 squared equals 3x squared minus 3.
X plus 5 squared equals 3x squared minus 3. You like that?
And then expand, and then move it over to one side.
Expand. I don't have anything out here I need to expand.
X plus 5 squared.
Oh, x plus 5. Yes, put that in brackets. This whole base to the power 2 is equal to this thing. That's just using your log a to the x of x is y. So that is to say a to the y equals x. So there's our y, there's our x, and there's our a, and here's our x. Okay, so now, then you just solve it. So we have x squared plus 10x plus 25 equals 3x squared minus 3. Oops. You send everything to one side. 0 equals 2x squared minus 10x minus 28. What's next, everyone? 0 equals x squared minus 5x minus 14. We have 0 equals x. Huh?
You just have to have the 2 in front, just like in brackets, right?
No, because I divided both sides by 2, you see?
Oh, yeah, and you divide.
So it disappears. That's one of the lovely things about setting a quadratic equal to 0, is when you divide both sides or multiply both sides by the same thing, you only have to do it to one side of the equation, because anything times minus 0 is 0. Okay, so 0 equals x minus 7 times x plus 2, and the cool thing is that gives you two things that both work, right? Because minus 2 is inside there, and positive 7 is out there. So both of these are valid. X equals minus 2 or 7. Oh, tricky example where a negative actually is admissible. Because you see we're squaring it here, so it will become positive. Yay! That's what careful working will do. All right, this one is the nice one, and then we get to the practice problem. So I'm going to pause here. You do this one yourself, find your questions, and then we will discuss it together. All right, this is the ultimate problem, so it's a good place to get stuck, everyone, because it's the last problem of the lesson. So let's unfreeze. Let's do it together. What's another way I could, well, okay, first of all, what do you know about cube roots and positivity and negativity?
Feel pretty negative about them.
You feel negative about cube roots? But do you sometimes feel positive about them and sometimes feel negative about them?
Pretty rarely.
B gets me. B knows that cube roots can both be positive and negative. Want me to prove it to you? Yes, Mr. Jennings, prove it to us. Go to Desmos, Mr. Jennings, and show us some more Desmos facts. Here is x raised to the power 1 over 3. Oh, I also gave away the second thing that I was going to talk about. Doesn't that just look like you took a cubic equation and rotated it? Almost like it's the inverse function for a cubic equation. Like if I had x cubed here, and then I showed you the line y equals x, you would say, wow, you just mirror imaged those two things. It's amazing how all this is so interconnected, Mr. Jennings. We sure are lucky to be able to study such interesting math in our senior year, particularly after midterm, when we're all locked in. So locked in. So, here we go. So, we can also rewrite this in an interesting way. I think you'll agree. I'll rewrite it in an interesting way. Log base 10, because it's not listed there, x squared plus 48x to the 1/3. All right, now, if this thing here that we take to the 1/3 is positive, then the output is positive. If it's negative, then the output is negative. So what can you tell me about the values of x that are admissible and inadmissible? How would you start that? How would you start investigating those? Someone tell me, just write it out, Mr. Jennings, and we'll figure it out together. And now with enthusiasm. So, you just write it out. You just go x squared plus 48. X must be greater than 0.
What about the 1/3?
Huh?
Do you still need the 1/3 or no?
We're going to get there. Well, see, what I was showing you over here is like when you have x to the 1/3, anything to the 1/3, if you have a negative input, the output is negative, inadmissible. If you have a positive input, the output is positive, admissible. So we need this to be true. X squared plus 48x is greater than 0. I think we could factorize. I think we can do that together. Is greater than 0. Oh, Mr. Jennings, I remember from Unit 3 where we made an interval table. And we noted that this would be like x equals 0 is one of the zeros here. And x equals negative 48 is one of our zeros. And then we tested. I recall testing. So here we have 0. Here we have 48, but it's negative. And if I test my function in here, I get a negative value. And if I test my function over there, I get a positive value. And if I test my function over here, I get a positive value. We're a little short on time, so I'm going to skip those tests, but I'm going to prove it to you in Desmos by writing this stinking function. If you can't visualize it, here it is. X squared plus 48x. Looks like this, everyone. There's 48, there's 0. Note it's negative in between and positive out there. Okay, so let's keep going. So now we know x is either less than minus 48 or x is greater than 0. Here's our two limitations. Almost like that Unit 3 stuff is useful for this stuff. Now, apply. Whoa, we want to lock in, everyone. Lock in. This is the last little bit. Help me with this. What can we do next? Do you want to do it the hard way or the easy way? Maddie, tell me the easy way. The easy way. The easy way is you listen the first time I explain it. Here we go. We're going to apply the power law. 1/3 of log x squared plus 48x is equal to 2/3. The next easy thing to do, multiply both sides of the equation by 3. Isn't that easier than equating that thing to this thing? Anyway, so then we get log of x squared plus 48x equals 2. And now what do we do to solve this? Quinal, change the form to exponential form. But this logarithm doesn't have a base. It's base 10, everyone. This is the common log. So that is to say 10 to the power 2 equals x squared plus 48x, which is also to say, folks, that 0 equals x squared plus 48x minus 100. Pretty, eh? Oh my goodness, that factors. 0 equals x plus 2 multiply x minus 2. Oh, how embarrassing. X minus 2 times x plus 50. Because I know two numbers that multiply to negative 100 and add to 48. And I know them real quick. Okay, now I find that x is either equal to 2 or x equals minus 50. I check. Minus 50 is less than minus 48. I check. 2 is greater than 0. Both of them work. And the people rejoice. Not only do they rejoice, but they do their practice at home for homework. Okay, any questions for me? No? Okay. Oh, no, that's the wrong spot to go to turn off the recording. All right.
I should say it right now.